Hi, Ernst.
Good morning.
Hello, hello. Well, we are here. We are all ears. Happy to see you again. Since this path, this journey, these complements, these complementarities, this whole great group somewhere, this whole great group which brings Modeste, or not from elsewhere, Pierre, to this edifice of agroecology. We are happy to be with you this morning. So is everything working well? It seems to be working.
Yes.
Good, great. Well, let's continue. We'll continue since we'll have a debate later where we'll talk about erosion, we'll talk about fertility, about fecundity. Marc-André has led us onto the path of fecundity. Aquifers, the issue of aquifers, of the resource, of the use, of the usage of water. And then with you, we're going to take a little tour in the forest and outside the forest with the trees. We're listening to you, Ernst. Thank you for being with us.
All right, so I'm going to ask you to load the presentation I sent you. Trees, forests in water management.
Okay, I truly think that the technical side of things is always very efficient and highly effective with Ver de Terre. So with a little bit of good luck, it should absolutely work at any given moment now. I won't even need to fill the time. There we go, that's perfect. Is it good? Do you have the feedback on your end, Ernst?
Yes, it's perfect. That's good.
Well, we'll listen to you for about 20 minutes. Afterwards, we'll have Olivier Husson. And then right after that, the highly anticipated grand debate here in Elne, live and, of course, worldwide on the Ver de Terre Productions YouTube channel. It can't be said enough. Thank you to the technical team. Over to you.
Thank you very much. Thank you for the invitation. So we're going to talk about trees and forests in water management and open up a few avenues for further reflection that can be explored in more depth during the debate. Trees, giants in both space and time, are truly a fundamental element that brings us into the realm of the long term. And on the next slide, there's something essential we need to consider. At the very beginning, let's go back to the previous slide. At the beginning, all of Europe was covered in forests. I always start with the same fundamentals. The forest is the natural operating mode of the Earth's ecosystem, of the Earth as an organism. Whenever conditions allow, 6,000 years ago, 80% of Europe was covered by natural forests. And we took agricultural land, in particular, from these forests along with their fertility. That's the first element that is absolutely crucial. Next, on the following point, we understand that this forest is not there by chance. The Earth establishes it wherever possible if the conditions allow. At the same time, it alters the environmental conditions through the establishment of these forests. So it's the Amazon basin, the Congo basin, which serve as protective envelopes that absorb moisture and solar radiation, transform that into biomass, and convert it into hydrological cycles. Now we're getting to the heart of the matter. Hydrological cycles are driven by the presence of forests. And that's why above Brazil, for example, there are about half a dozen cycles of evapotranspiration and precipitation above the forest, with a pump effect that draws maritime air masses from the Atlantic over the Amazon rainforest. And all of this will migrate. It's a vast atmospheric river, a flying river, that will then be diverted northward to North America and southward to Argentina, making those regions much more temperate and humid. So specialists, Makarieva and Gorchkov, refer to it as a climatic heart, a biotic pump. Forests truly form an essential system at this level. In the boreal zone, forests also play a similar role, but there it's more about storing heat. We could discuss that in another context. Next slide. And here, what's interesting are the comparative curves developed by Russian researchers. On the top graph, which I can point out here, we have a representation of the Amazon basin with the Atlantic and the Pacific. And here, this is the Congo basin. Let's say we're at the equator. And the comparison of precipitation over forests versus precipitation over the ocean is interesting. We have a logarithmic scale. And when the value is 1, there is almost 3 times more precipitation. When it's 2, it's 7.4 times more. So here we're between 1 and 2. That means that over the Amazon forests, there is actually 3 times or even more than 3 times as much precipitation as over the Atlantic. The same goes for the Congo Basin. We are below 0, which would be equal. And it's the same for the boreal forests, with a difference between summer and winter. In summer, there is a surplus of precipitation compared to the ocean at the same latitudes. The opposite is true for Australia, where it is much drier inside the continent. And this is linked to the fact that it is completely deforested. So this is an absolutely essential illustration, the demonstration that the forest causes precipitation much more intensively than areas without forest or even just the ocean continuing. There you have it. And here, the Czech and Slovak researchers, Kravček and Pokorny, have developed a new paradigm of water by understanding that the presence of vegetation is absolutely essential for the climate. And the fact of having eradicated this vegetation to replace it with agricultural crops has completely transformed the dynamics of water exchange as well as energy exchange. When it comes to solar radiation, above areas saturated with water and rich in vegetation humid zones like the Amazon, for example, is an enormous amount of evapotranspiration. There is a heat flux that is emitted by this vegetative cover. There is a heat flux that enters the system and a little bit of reflection. In comparison, in open drained areas, which are in fact tragically drained by these lands that can no longer store water, we no longer have the amount of evapotranspiration that would send energy back or transform it. Instead, we have a heat flux. These fields are essentially heat islands, like the ones we talk about in cities. They have much less evapotranspiration. It's really the opposite situation compared to what the forest does. A little bit of reflection and some transfer inside. So it's the reversal of trends, reduced evapotranspiration and increased heat emission. So here with these open areas that are always either too dry or have to be artificially irrigated, they are basically radiators, emitters of energy and heat. So we even have a greenhouse effect in this form. Here, this shows with figures that these researchers have very clearly analyzed the difference it makes to have eliminated trees from a system or to have them really present. There you go. Next slide. And here, with current visualization techniques, this is infrared photography, are able to show that when you have a surface, even just 1 square meter, the square meter that Alain Canet is so fond of, which spontaneously regenerates with vegetation. When vegetation has already managed to colonize certain areas, it appears blue under the infrared camera, whereas entirely mineral zones appear red and yellow, indicating that they emit heat. So here again, we have a very clear argument in favor of covering agricultural and forest soils and so on to stay cool and to stop emitting heat. So this coolness is naturally due to evapotranspiration. This is the water flow at the level of the individual plant. There you go. Next slide. So here, we've often discussed this idea of the forest as a sphere that's able to protect its interior from the outside, store its water, and prevent winds from passing through the forests thanks to a closed canopy and an edge. That doesn't mean it's a completely protected forest. It's a forest that can be managed, but by removing the trees, by harvesting them one by one individually, while avoiding as much as possible creating large gaps of heat and light on the ground, the entire forest interior needs to remain somewhat shaded, and then the trees can move into the light channels that we create. Next slide. The next slide actually illustrates the hydrological relationships connected to this sylvosphere. The precipitation we mentioned earlier, which is already to some extent a result of the forest's presence, is thus received by the forest in return, and it only uses a part of it. That's why there is still an Amazon River that flows out of this forest. Only a portion will be used by the forest itself, 2/3 or half, for biosynthesis, for this process of evapotranspiration, this overall cooling effect. And the rest of the water, compared to 100% of the precipitation, will percolate into the subsoil, feeding the groundwater, rivers, and so on. And here we have physical rivers that flow in one direction. And as we've seen, in the other direction, we have flying rivers, atmospheric rivers, also created by forests. So we have here two hydrological flows that are extremely interconnected and operate thanks to the presence of the forest. So here are a few figures. All of this is, of course, due to photosynthesis, thanks to photosynthesis. Solar energy is transformed into chemical, or more precisely, biochemical energy. But the real gift in all of this is naturally the water flows. 300 kilos of water are needed to produce 1 kilo of organic matter. And in addition, half a kilo of new water is formed. We've discussed this elsewhere, but these 300 kilos of water are for an average tree. Annual plants require much more water to produce dry organic matter. And some trees are much more frugal from that point of view. That, for example, is the value for beech trees. But if we take Scots pine, it is capable of producing 1 kilogram of organic matter, according to some authors, with only 100 kilograms of water. That's why it's the champion competitor in extremely exposed environments like rocky cliffs and karst areas. It's still always the choice of downy oaks or Scots pines that get established, because they really need very, very little water. And with that, they produce organic matter, soil, and prepare the ground for the trees. Here is the next one. So we have these interesting phenomena, which we also see in this drawing by David Delas, the phenomenon of hydraulic lift. When it's very hot, the tree makes sure to stay alive. It will be able to seek water deep down and supply the roots that are too hot, that couldn't put on sunglasses, but can receive water coming from below. And these roots will transpire just like the leaves do through evapotranspiration. And this transpiration will moisten the soil and partially supply the crops above. So here we have rain that actually comes from below, provided that these roots are present and deep enough to compete with the roots of agricultural crops. Next slide. So deforestation is known to be the mark of many civilizations. Here, the image is from a region in Bosnia and Herzegovina. And in the past, in the same region, there was also a karstic area, very challenging, but extremely fertile and powerful forest stands had managed to establish themselves. And their human greed turned it into planks by clearing everything without really practicing forestry that respects the forest by maintaining the forest cover and harvesting only what the forest provides. But by clearing the forest, we ultimately completely transformed and devastated the landscape. And now it's no longer rivers of water that flow, but rivers of stones that come out of these regions. All the humus has long since been washed away. This is what happens when forests are removed. A very interesting experiment was conducted to quantitatively show the difference between a small watershed of a certain area, 1 or 2 square kilometers, at most of which was completely forested, compared to another that was partially deforested for pastures. So this is still very gentle, entirely natural, but even this difference already showed that the forested watershed, the Sperbegabenant, the partially deforested one, the Rappengraben, were distinct. And here you can see that at the outlet of these watersheds, there were measurement stations for the effluent from both watersheds. It was observed that not only the intensity, but even the timing of the river flow coming out of these watersheds was very different. So climatic extremes are immediately amplified when there is deforestation, when forest cover is reduced. Next slide. And this, of course, gives us tools to restore what we have done so far. Artificial forests, for example, are often exposed to all the winds. We now understand that the most important thing for this forest is the water in its soil. Even if it is an artificial plantation, we must allow it to manage its water extremely efficiently without letting it dry out from passing winds, by restoring its edges, by observing how the trees function. And this will allow these edges to be colonized by wildlife, which will bring seeds back into the forest. And we will once again have a natural regeneration cycle in this forest, starting from an artificial forest. So it's relatively easy to do. And this should be a priority suggested to forest planners, even when working on industrial or semi-industrial plantations. Let's continue. So that's water management for forests, but water management is becoming increasingly problematic in our so-called agricultural deserts. And here, as we understand, the goal of agroforestry is to restore some structure, a network of forests, hedgerows, and biodiversity corridors to a portion of the land, to protect this land, to restore its water supply, but also, for example, the dew produced by these trees. They therefore have their powerful evapotranspiration. This creates dew that is captured by the plants. And here we have a water quality that is truly remarkable, which deserves to be studied more closely. This first water, which receives the sun's initial rays, has unique properties that remain to be discovered. So here we have some truly interesting phenomena to restore phenomena that will benefit the crops, which here have become far too artificial compared to their original state, as these soils were initially rich in organic matter and protected by trees. Next slide. So the landscapes will be able to evolve. Agricultural deserts will be enhanced with hedgerows and wooded strips. Here we need to envision individually planted trees to provide shade on a case-by-case basis. It's both about individual trees, but also about corridor-like systems where interaction with wildlife is possible, where bats can come and hunt mosquitoes within the urban area. All of this is a win-win situation. We've already begun to understand the need to replenish the groundwater table. Yes, in large alluvial systems, and to give rivers more space so that water flows more slowly, allowing the groundwater table to recharge over the necessary period. And when there are floods, we also have much larger retention basins that benefit these marshy areas rather than water rushing through quickly without benefiting anyone. Next slide. So the question always comes up, but how many trees will we need to replant? And here it's not about making a sacrifice. It's not about sacrificing farmland for the sake of trees. It's about saving agricultural land that is threatened by erosion, by drying out, land that has to be artificially irrigated by pumping. All of that costs money. These are soils that are declining in fertility. So it's about replenishing these soils with organic matter at ground level, but also protecting them laterally with hedgerows. Here, there's an interesting law, the famous Pareto principle, which promises much faster results than we might think, since with little effort, 20% of the effort, we already achieve 80% of the results. So will we need to return 20% of the land to a natural state with planted species? It could also be orchards. Productive species, or will 10% be enough? Of course, in some regions, we're starting from 0%. So what will happen with 5%? What will happen with 10%? And then gradually observations will show us what is necessary. But the results are very, very quick in all these experiments that have already been done. Next slide. There you go. What we did with Lampedusa used to be an island covered with trees. And the observation here as well is that part of the rainfall has disappeared. there was a decrease in precipitation on this island from the moment it was completely deforested. And today it is entirely dependent on the mainland for its water supply, I believe. In comparison, at the same latitude, the southern coasts of Turkey are still forested, and there you find biological marvels. There are even bears that inhabit these coasts. These are magnificent areas and very interesting from a tourism perspective. It's much more profitable to have coasts like these, both for tourism and for wildlife naturally, than to have desertified and artificial islands like those. Next slide. There you go. Greening dry regions, we're talking about Mediterranean areas. These are naturally scrublands, areas that are extremely poor in rainfall. So it's about capturing as much precipitation as possible on site, channeling the surface runoff directly into ditches along contour lines. These are the modern systems for planting trees. And here we force the water to penetrate, and the tree waits for the water with strong roots to create biodiversity and to carefully retain that water. So here, these are reforestation trials that have taken place. I have a friend who worked and still works in India, who managed to make rivers flow again using systems like these. Let's not forget the ancient wisdom in these regions, terraces. And here we should invest the last drops of fossil fuel in mechanical means to shape and restore these terraces, which have the ability to capture the maximum amount of water instead of letting it run off the surface. With tree borders to provide shade, hedgerow borders or hedges that should complement the terraces, in my opinion, to also bring biodiversity in this way. I would like to mention the famous Sepp or Josef Holzer, the Austrian, who even worked in mountainous regions by installing retention basins at the top of cultivated areas to hold water and then let it percolate down into the lower areas, adding to the beauty of the organic structures, all with remarkable efficiency. He tends to talk more about permaculture, but it's along the same lines as what we do in agroforestry. Next slide. So just one more word about another connection trees have that goes beyond the sky with clouds and precipitation. It's their connections in the cosmos. Trees are connected to these energies. We notice this in all the research we do from the perspective of lunar influences, for example, chronobiology. And here, a very important aspect for restoring the hydrological cycle is illustrated in the next slide. Next slide, please. These will be those immense reforestation projects. 350 million hectares have already been reserved or pledged by governments according to the Bond Challenge. All of this will require a lot of nurseries. And here again, the most modern science, specifically the one that integrates chronobiology data now, allows us to manage nurseries by knowing exactly when to sow in order to achieve maximum water absorption by the seeds, to ensure the highest efficiency of sowing, to maximize the vitality of the plants, and then to replant them. This will probably also be much, much better when this particular action also fully respects the natural lunar rhythms of the various plants, species by species, you see. All of this still needs to be studied further, but when it comes to germination, it is already recognized that it plays an essential role. So that's what's in store for future projects and for the new hydrological cycles that we will also implement as we fight against the advance of deserts and dried out areas. The next and last point is to show that the future is already here behind us. We just need to look back at what the pioneers did in Uruguay, as was beautifully photographed by Jan Arthus Bertrand. And these projects are, of course, about carbon forestry, carbon agronomy, but at the same time, they're also about agronomy for effective hydrological sites, both locally and globally. That is what I wanted to offer as a reflection within the allotted time, I hope. Thank you.
Thank you very much. Thank you once again, Ernst. We truly appreciate your presence here today. Applause in the room, applause from all over the world as well. Thanks to this connection on YouTube. I used to think that YouTube was only for rock and roll and disco, but apparently there's also water and Zürche. So to sum it all up, can we say that trees hydrate dry environments, Ernst?
When trees hydrate dry environments, you really have to look at things in detail. In a dry environment, you can't just start in the middle of it. You have to look at where there is still vegetation. Because generally, these dry environments were once wooded or covered with vegetation. We've seen to what extent, and once we've recognized that, we can answer this question in a concrete way. Go to where there is still vegetation, where there are trees, and plant these new trees very close to where vegetation is already possible. And by planting tree after tree, it will be possible to make gradual progress. It's important to have trees of a certain size. Simply sowing would be easy, it wouldn't be bad, but in dry environments, it's not possible. That works in forests. When the humus is ready, when there's moisture, there you can sow, but in dry environments, you have to plant because the seeds are too close to the surface and don't have access to water. What you need are young trees that you'll support during the first year, because when you plant them, you set their root system at a certain depth, and at that depth, the water you provide will benefit them in the first year. Gradually, they'll establish a hydrological cycle for themselves and make progress tree by tree. That's how we'll be able to move forward thanks to trees of a certain size right from the start.
Thank you very much. Thank you so much. We'll see you again a bit later anyway for the debate, for the big debate, this long-awaited discussion. Thank you for reminding us about this square meter policy, about this model of the forest that we try to copy and imitate. Sorry, and in the end, we're actually managing it quite well fundamentally. Thank you for reminding us that erosion is the scourge of our civilizations.